Hello and welcome to this lecture on purification and separation methodologies. In today's lecture, we will develop a very important equation called the resolution equation. Resolution equation depends upon three very important parameters or characteristics called capacity factor, selectivity and efficiency. And then in the later part of the discussion, we would use these three parameters separately and try to optimize chromatographic separations in a chromatogram. So, let us begin. In order to resolve a chromatogram in a minimum time, and this is one of the chromatograms which we have become quite familiar with, we know that the resolution equation, as we have discussed in previous lectures, is equal to 2 times TRB minus TRA upon WB plus WA, where TRB and TRA are the retention times of peak B and peak A respectively, and WB and WA are the peak widths of these two peaks. Now, we are talking about two peaks and we would like to resolve these two peaks which lie very close to each other, which means that once the peaks lie close to each other, the spread of the peaks is going to remain more or less the same. If this is the case, then we can safely assume that WB in this case would be more or less equal to WA. Now, if you consider this, then RS can be construed equal to twice times TRB minus TRA upon 2 times WB. This 2 and 2 will cancel out, so you get a final equation which is RS equals to TRB minus TRA upon WB. The point to be noted here is this twice WB could have been twice WA, but we want this equation in terms of the peaks of this peak of B, hence we are keeping it WB. Now, I want you to keep this equation in mind, because now in this next equation we know that number of plates is equal to 16 times TRB upon WB whole square, that we have established in the previous slides. Now, in this equation, if we would like to get the value of W, so the value of W would come out to be 4 TRB upon N under root. So, what you basically do is you transfer this square to this side and transfer this 16 to this side and then get the value of WB out. Now, we know that both the equations are in our hands now. So, we can put this value of WB now into this equation of resolution and see what we get. So, if you put this value of WB into this equation, your equation for resolution becomes square root of n times TRB minus TRA upon 4 TRB. So, as I was mentioning in the previous slide, this equation of resolution has to come out in terms of three very important variables on which we have seen in previous lectures resolution entirely depends. One of those factors is number of plates or plate height, right. So, now if you look at this equation has already a value or a term which will account for number of plates or plate height. Now, we are left with the other two terms. One is capacity factor and the third term would be selectivity factor. So, we need to bring in capacity factor here into this equation now. Let us see how we would do it. I would like you to remember this equation for the time being. We will use it now. So, we know that capacity factor for any given peak is given by K equals to Tr minus Tm upon Tm, right, that we have established. Now, using this equation, you could find out the value of Tr. So, this Tr could be equal to Ktm plus Tm, right, that is simple. Now, keeping this value in hand, this Tr could be Trb or could be Tra, right. So, we put this value of Trb and Tra into the previous equation of resolution. If you put these values here, the new equation comes out to be as, so Rs equals to square root of n times Kb Tm plus Tm, which is your Trb, minus Ka Tm minus Tm, which is your Tra, upon 4 times Kb Tm plus Tm. Now, in this equation, both these Tm terms will strike out, and also you can take this Tm out of the bracket and also this Tm here out of the bracket. So, what you are left with is square root of n Tm times Kb minus Ka upon 4 Tm Kb plus 1. Again, in this equation, this Tm term will cancel out. So, what we are left with is Rs equals to square root of n times Kb minus Ka upon 4 times Kb plus 1. Now, look at that equation. In this equation, previous to the equation we discussed in the last slide, we have been able to incorporate another additional term in addition to the number of plates, and this term is capacity factor, right. So, now we have two very important parameters on which resolution depends: plates, number of plates, and also the capacity factor. Now, we are left with the third important term on which resolution depends, and that term is selectivity. Let us now try to bring that term here. So, from the previous slide, we know this Rs is equal to square root of n times Kb minus Ka upon 4 times Kb plus 1. Now, we do a small mathematical trick here. We multiply and divide the numerator term here by Ka. What is achieved after doing this is the following. So, you get Rs, which is equal to square root of n times Kb upon Ka minus Ka upon Ka, which becomes 1, times you multiply the same numerator by Ka upon 4 times Kb plus 1. Now, we had seen in the previous lectures that selectivity factor alpha is equal to Kb upon Ka. So, if you put this value of alpha in this above equation, you would get Rs equals to square root of n times alpha minus 1, alpha is here, minus 1 times Ka upon 4 times Kb plus 1. Now, in this particular equation, as you would appreciate, we have been able to incorporate all the 3 integral parameters. That is, this equation contains a parameter for plate number of plates, it contains a parameter for selectivity, and it also contains a parameter for capacity factor. But if we look at it closely, we see the capacity factor for both the peaks are retained in this equation. So, we can further simplify it, and let us see what we are going to do now to simplify it further. Now, in the same equation, we play another mathematical trick, and what we do is we multiply and divide this equation by Kb. So, if you do that, what happens? Rs equals to square root of n times alpha minus 1 Ka upon 4 times Kb plus 1, that is your original equation. Now, if you multiply and divide this equation by Kb, you get Kb term here and you get another additional Kb term here. Now, there is a significance of doing it, because if you look at this term Ka upon Kb, this is reciprocal of your selectivity, because your selectivity term is Kb plus Ka. So, now you can put this selectivity term back in this equation and one can get the final value, which is Rs equals to square root of n times alpha minus 1 times Kb upon 4 times Kb plus 1 alpha. Now, this is the final equation for resolution that we would use for further optimization studies. Basically, all the 3 terms in this equation signifies 3 very important phenomena associated with chromatography. This term square root of n times 4 talks about efficiency of a particular chromatogram, right. This term alpha minus 1 upon alpha talks about selectivity of a particular chromatogram towards the pair of solutes you are interested in resolving. And the third term talks about capacity factor, this Kb upon Kb plus 1. It talks about the retention of the peak in question to the stationary phase. What is their physical significance on a chromatogram? Let me show you this chromatogram, which looks a little bit complicated, but I hope I will be able to simplify it for you. Now, if you look at the peaks here, I will try to explain it in terms of the 3 factors we have got from the resolution equation. Number 1 is capacity factor. So, what capacity factor tells you about this pair of peak, for example, is basically how long one of the 2 peaks get retained on the stationary phase, right. That is about capacity factor. If you talk about selectivity, which means, now let us consider these 2 peaks here. So, in these 2 peaks, by selectivity we mean how well these 2 peaks are separated from each other on the detector's response on this chromatogram, which means how much is your stationary phase selective towards one of the 2 peaks, all right. And the last term efficiency talks about the morphology of the peak which has come out. It means, for example, in these 3 peaks which are at quite a good distance apart, we can still see the peak width and find out how efficiently the peak has come about. The significance of these 3 terms in a practical manner in a chromatogram is that you could always have, for example, a very selective chromatogram having 2 peaks quite at a distance, but then it may not be efficient. It means the broadening might be more than expected. Likewise, the capacity factor might not be a good capacity factor, and you would like a peak to come out a bit later or a bit earlier. So, all these questions can only be addressed if we would have in our capacity something through which, or parameters through which we could handle, manipulate and govern all these 3 factors: capacity factor, selectivity, efficiency, quite independently of each other, and get a very well resolved chromatogram, and that is the purpose here. So, the next part of the discussion is about optimization of chromatographic separations, and then try to manipulate and modulate all these 3 important parameters quite independently to get the desired resolution for a pair of solutes. Let us try to first manipulate capacity factor K to optimize resolution. Now, we know that capacity factor is equal to Tr minus Tm upon Tm. It means that your K, it is related to a resolution that we know from the previous equation, right. But in this equation it also tells you that K is directly related to your TR, which is your retention time. So, it means it is very important for us to see that by changing K we can certainly manipulate resolution, but we would also need to see in equal measures as to what would be its impact on the retention time. Because as a chromatographer's goal and as a chromatographer, we would always like to optimize the resolution, but that should be attained in a minimum time. Okay? So, now let us try to see the impact of capacity factor on resolution and retention time. Here is a graph which tells you about the variation of relative improvement in resolution and relative change in TR, which is your retention time, as a function of capacity factor. Okay? So, this part of the curve in this graph tells you about variation in resolution as a function of capacity factor, whereas this curve tells you about variation in retention time as a function of capacity factor. Now, there are certain important things which we can infer from this graph. So, in this particular chromatogram now, let us assume that the original capacity factor was 1 and you change that capacity factor from 1 to 10. Now, look at its impact on resolution. Resolution now from 1 gets increased to 1.8, which means that it has enhanced to a significantly 82% margin, which is quite significant, right. Now, what impact would it have on the retention time? If you look at this part of this curve, it tells you that the retention time gets increased by 1.6 times. So, then it is not so huge as compared to the amount of resolution which is achieved. So, the effect, if we could generalize this, that the effect of capacity factor is greatest if original value of capacity factor is small. For instance, it was 1 and it gets changed to 10. Now, let us assume that capacity factor in this case is enhanced further and this value of capacity factor is now 20. If you note now the enhancement in resolution, enhancement of resolution is not that huge. So, you gain only 8%. You get now 90% of resolution, as previously you were getting 82%. Whereas, retention time has now become double. It was 1.5 times and now it has become effectively 3 times. So, we could make an observation that a very large increase in K value does not significantly improve RS and also increase retention time significantly. So, then what do we do? This is what we have just seen in that graph. Now, we have these two manipulations which we did. In one case we enhanced capacity factor from 1 to 10 and the impact on resolution was that it got changed to 1.82 and retention time got changed to 1.5. In the next case, capacity factor was enhanced to 20, resolution was enhanced to 1.9 and retention time was enhanced to 3 times the original value. Certainly, we can make an observation that in this particular case, we have optimized capacity factor better than in this particular case. So, if I remember and if you could remember also, in some place in some of the lectures I told you that the good value of capacity factor is between 1 to 10 and this particular equation now proves why we should keep the value of capacity factor up to 10. Now, another important question is, we now know that the value of capacity factor optimized one should lie around 10, but then how do we achieve that? Because see, there is a very important pertinent question which you should also keep in mind. Now, we want to only manipulate capacity factor independent of other two factors, which is number of plates and selectivity. and you know that selectivity depends upon capacity factors of both the peaks, right? It is Kb upon Ka. So, what you would want if you would like to only selectively manipulate capacity factor, that can occur only if you change capacity factor by equal proportions for both the peaks, because in that case your selectivity factor will remain the same and only capacity factors will change, right. So, in gas chromatography the way we used to do it is by decreasing column temperature, because what happens is when you change column temperature, decrease it, so then solutes vapor pressure will also decrease, and then it would tend to spend more time in the stationary phase, and effective capacity factor for both the peaks or for all the peaks will change, it will increase, right. For liquid chromatographies, you can change the mobile phase strength, and that is the easiest way to change capacity factors. So, one would reduce mobile phase strength, and that would mean your solutes will spend more time in stationary phase, and that would mean capacity factor would increase, right, and this capacity factor would increase for both the peaks in question, right. Now, let us take the second factor, which is selectivity, and let us see how to modulate selectivity to optimize resolution. One could easily observe that change of the selectivity factor alpha has a more dramatic effect on resolution than changing capacity factor, and this can be proven by the following two equations. Now, let us say in this particular equation we have an alpha selectivity factor 1.1. So, if you solve this, you find the value of resolution comes out to be 0.09 times all the factors remaining constant. Okay. In the second case, you change this value of alpha from 1.1 to 1.5, not a huge change, right, but once you see the resolution, it turns out to be 0.33 times all the factors keeping constant. What does it mean? So, it means the change in resolution is 0.250, which means that your resolution is improved by 250%. Now, that is remarkable, and this is what we mean when we say that this factor has a dramatic role in optimizing resolution. Having said that, there is a word of caution. It is not easy to manipulate selectivity factor for the following reason. Now, you know that your alpha is equal to Kb upon Ka. So, unlike what I said in capacity factor while we were modulating capacity factors, in this particular case you would want one of the capacity factors of two peaks in question to change differently from the other peak, and that, having said that, is not an easy thing to do. So, what we need to do here to change alpha, either we change k of one component and not the other, or we change both the components, but then both the components capacity factors should be changed differently. Now, how do we then do it? There are a couple of ways through which we can achieve this kind of selective change of capacity factors. Okay. In especially liquid chromatographies, we need to look at what we call secondary equilibrium reactions of your solutes with the stationary or mobile phase. What do we mean by that? Let me show you by this particular chromatogram, this example. You have these two components here, one is para hydroxybenzoic acid and another is para aminobenzoic acid. Now, both of them are being eluted in water. So, it means their polarity is almost the same, and hence its interaction with the stationary phase and mobile phase are going to be more or less the same. Now, if you check their elution at a pH of 5, you see that the value of alpha, the value of selectivity is 1. It means there is no selectivity for any of the two components, both components are eluted at the same time. So, that is about their primary equilibrium established with the mobile phase, which is water, and the stationary phase. Now, what happens that if we change the pH from 5 and we start to lower down the pH? If you lower down the pH, you would notice that both these compounds starts to interact with this aqueous compound, this aqueous mobile phase differently, and starts to generate a difference in selectivity factor. Now, that something is secondary equilibria, which is being established with the mobile phase and stationary phase vis-a-vis your solute. This is what we can do to change the mobile phase in order to change the selectivity. For gas chromatography, though, as you know, we cannot do anything with the mobile phase. So, the only thing left to us is we would need to change the stationary phase, and you would all appreciate that this is not easy, right. So, in liquid chromatography we can change composition of the mobile phase, but in gas chromatography we would need to change the stationary phase. Hence, it is not a very good parameter to be tampering with. Okay. Last thing about this selectivity factor is that if you note this particular table, you would realize that as the value of alpha starts to increase, this value of selectivity in resolution equation starts to approach the value of 1. It starts to approach unity, which means if it approaches unity, it would mean that at those values Kb would more or less become equal to Ka, and resolution will start to become very poor, even if you change the other two parameters. Hence, we must make sure that for optimal resolution, your value of selectivity should lie between 2 and 5. So, now let me come down to the last parameter, which is number of plates n or plate height h, and how that impacts resolution in that resolution equation. This we have seen in the previous lectures, that as the number of plates of a chromatographic column increase, or as the height of theoretical plate decreases, in both the cases efficiency of the column is increased, and hence resolution in that resolution term will also increase. So, seems simple. So, what we need to do is that we should increase number of plates in a chromatographic column. Easy, right? One obvious way which can come to our mind is that we should increase length of the column. So, if you increase length of the column, automatically number of plates will become high. But is it advisable? It is not, for two reasons. You cannot indefinitely increase a column, right, the length of the column. It cannot be like 20 meters of a column you are using for a particular resolution. And then secondly, that is going to increase tremendously your retention time. So, that second aspect you must keep in mind, because I told you as chromatographer's goal, you want your resolution in minimum retention time, right. So, then what is the alternative? Your alternative is that you decrease plate height, and if you are able to do that, you won't need to change the length of the column, and the analysis time, which is your TR, would more or less remain the same. How can we do that? This is something we had seen in the previous lecture, which was Van de Metier equation, and one of the outcomes of Van de Metier equation were that one can always change the mobile phase velocity u, and one should aim at getting a value of u at this region, which is a very sweet value of mobile phase velocity, which is called optimal mobile phase velocity. And if one reaches this value of optimal mobile phase velocity, this is the point of maximum column efficiency, and you get the least height of the plates here, right. Now, once we talk about this, we also should know that the equation Van de Metier equation is not exclusive, and there are other equations also which should be kept in mind just to get the same term, mobile phase velocity. One such equation was given by Hawks. It is just some minor modification into this Van de Metier equation, and likewise Knox came out with another equation which was again certain modification in the terms used in Van der Meer equation. So, over and above, we must keep in mind that all these three equations have been used to characterize chromatographic systems, and none of the single equation can provide you best explanation in all the cases. You may need to use one equation or the other at certain instances. But the point is, with these equations you can always look for that sweet optimal velocity which gives you the least plate height for your best resolution. That is about your mobile phase, right? So, can you do something to the stationary phase also? Yes, we can, and that also we saw in some of the previous lectures. The way we change or modulate this column efficiency by changing height, modulating stationary phases by changing column packing. Since we know both the constants A and Cm, A stands for multiple paths, constant for multiple paths, and Cm for mass transfer in mobile phase, which are both functions of the size of the particle. So, then if you decrease size of the particles, your column efficiency will always go up, but then the point is there an extent, is there a limit? And yes, there is a limit, because if you decrease the size of particles beyond a limit, you would incur large pressures to push mobile phases through the column, and then your column will not work as expected. The other thing one can use is forget about solid stationary phases and get thin films of stationary phases. To this end, one can use capillary columns in gas chromatography or bonded stationary phases in HPLCs. In both the cases, this CS term, mass transfer in solid in stationary phase, would become 0, since you do not have a solid stationary phase, and hence you would be able to change the plate height to bare minimum, and then the column efficiency would be very high. So, to summarize this resolution equations and the optimization of resolution equation in terms of all the three important parameters, I have taken up this graph here, and this graph tells you about variation of resolution in terms of all the three factors: selectivity factor alpha, number of plates n, and capacity factor k. Now, as you look at this graph, it is very easily obvious and that changing this selectivity alpha has the most prominent and dramatic effect on resolution. It is more or less linear, right? Whereas, for rest of the two parameters, number of plates and capacity factors, they change resolution to an extent, but afterwards their impact on resolution does not remain very high. So, after a certain value their influence is not significant, but at the end there is an optimization. So, you are looking at a sweet value of all the three parameters, and it is not the maximum value. So, always remember, when we talk about optimization, we are not maximizing, we are getting an optimized trade-off value of the parameter which gives us the best possible solution. With this, we have come close to the theory part of chromatography, and in the next lecture I will take you to the world of gas chromatography, and I hope to see you all in the next lecture and join me for this discussion. Thank you very much.